Welcome, everybody. It's a great pleasure to welcome you to the CQCT seminar. Today, our speaker is Benoit Voisin, who is from the University of New South Wales and SQC. And Ben will talk about a perspective on skin qubits, which is all about material development, fast measurement, and modeling. So it's quite a broad scope that involved a large number of people. Ben, please take it away.
Thank you, Sven. Hi, everyone. Today I'm going to talk about basically what could be considered as a review on spin qubits in silicon, talk about a bit of history and recent progress. And this talk is basically tied to a review article that we recently published in MRI's Bulletin in the July issue, together with Joe Safi, Rajiv Brahman, and Sven Rock from UNSW. And Joe's left us, took an associate professor position in UBC about 2 years ago. Something that works. So here we go. So I'm going to start with a bit of history, as I said. So there were two major proposals in 1998 to use spin qubits as a platform for quantum computation. The first one was proposed by Lars and DiVincenzo, and the idea there is to confine electrons using electrostatic gates the same way. Those gates work the same way as for silicon transistors, and using the spin degree of freedom of those confined electrons, we can try to perform quantum gates and quantum operations. The advantages of such platform to use electrostatically defined quantum dots is that it uses very standard nanofabrication used by the CMOS industry, which come from the CMOS industry, so it's quite straightforward to do batch fabrications of these devices, and also very tunable in terms of their properties, in terms of confinement potential and the interaction between the quantum dots. So that's a key advantage there. The second proposal is very specific to silicon. It uses aims to use phosphorus dopants as the main player for quantum computation, and more particularly to encode the quantum information in the nuclear spin of those phosphorus atoms, and to mediate qubit or two-qubit interactions using the exchange between the electron spins around these phosphorus atoms. So the main advantages is that these atoms are known to yield very long coherence times, record coherence times in the solid state, and as I just said, can benefit for both electron and nuclear spins to have complex protocols and try to encode information this way. So following this proposal, there's been over 20 years of work until today. I'm just giving a very, very brief review of some key dates that happened and that led us to today. The first pioneering work started in the early 2000s up to 2010. It was mainly to basically characterize the confinement of these electrons in either on single dopants or trapped in quantum dots. So there's the seminal work from Carver-Noven demonstrating Coulomb blockade in a gallium arsenide quantum dots, and that basically drove to a key result in 2007 to demonstrate coherent oscillation using a gallium an electron trapped in gallium arsenide. In parallel, there was already work being undertaken in silicon systems. So I show here the example of the characteristic of a transistor device when it's cooled down. You can see that it basically creates a quantum dot underneath the gate, and we can observe Coulomb diamonds and Coulomb blockade in these transistors. And they were so this particular device was directly taken from the CMOS industry, but there was also work being undertaken to make homemade silicon transistors and silicon quantum dots. But I would say at that time, gallium arsenide system had the advantage, had the lead in terms of quantum computation, up to, I would say, 2014, which was a real swing for silicon computation towards silicon systems, with the demonstration of very long, extremely long coherence times using isotopically purified silicon. So that was both for single dopants in silicon, single phosphorus dopants in silicon, and also most quantum dots in silicon. And basically, of course, there's been more work being done, and that really led us up to today with very complex devices that can involve different set of materials. So there's silicon MOS, there's silicon germanium, and phosphorus dopants in silicon, as two examples given here. And using these devices, there has been major milestones that have been achieved. So as I just said before, long coherence times, demonstrating a CMOS qubit, fast 2-qubit gate, fast operations on nanosecond time scale, and very high fidelities beyond 99%. And also the first steps towards scaling up with multi-qubit devices. So the question I want to address today is, how did we get there? What happened? What has been developed? What are the key achievements to enable this type of very complex devices? So the way progress has been made in these devices is to go through a feedback loop that comprises three main components. The first component is the ability to create and address quantum states. So it really ties up to fabrication techniques and material developments. You need to be able to create a device that you are confident are gonna confine an electron one way or the other, and you're gonna be able to address this electron and eventually perform operation. The second part is really exactly the second component of this feedback loop, which is the ability to manipulate these quantum states, and that ties up to the development of electrical techniques to address the states. And the third component is to understand what you're doing, basically, and understand how these quantum states behave, and that ties up to a modeling and characterization part of the device. And once you've completed these three components, you can go back to the fabrication step and basically try to fabricate a more complex device with optimized capabilities, and basically you go through the loop over and over, and this is how you create more and more complex devices with better and better performance. So this feedback loop is pretty much common to any quantum computing platform. Of course, each of these platforms would come with their associated challenges. So what I want to do for part of the rest of the presentation is to basically take single dopants as an example of what were the challenges and how they were tackled throughout the time. In particular, for silicon qubits, there is a big challenge, which is to deal with a valid degree of freedom. So, for example, the dopant ground state is often represented in Fourier space, this little diagram here, with a wave function that is located at a finite momentum, k mu, highlighted by these ellipsoids there. For the quantum dots, there's also a valid degree of freedom that's very important. And the challenge there is to control what's happening at the interface between different materials, for example, here between silicon and silicon germanium, with a possible presence of interface steps which can disrupt the valid degree of freedom and disrupt control of the valid splitting between the ground state and the first excited state. So I'm going to go back in time again and just say that how can we just spend a bit of time to how can we address a single dopant in silicon. So the first idea was really to leverage the work done in microelectronics. So of course, there was Moore's law, which basically tells us that the dimensions of these transistors were getting smaller and smaller, up to the point where single dopant effect could be observed in these transistors. So from the microelectronics industry, this was a big issue. They didn't want to have the single dopants because that yield to an increase in viability of the transistor's performance. So basically, they just simply got rid of the issue by getting rid of doping in the channel. But for quantum physicists, this actually represented a big opportunities to basically, hey, we have these single dopants in channel. Let's try to address them and control them for quantum computation purposes. So the first experiment that basically showed to how we can address these single dopants in transistors was to evidence single electron transport through a single dopant from the source of the transistor here to the single dopant and then to the drain of the transistors. And you can basically control the chemical potential of the dopant using the gate voltage of the transistor. And so if you measure the internal current flowing through the transistor as a function of the gate and the bias voltage, you can evidence these Coulomb diamonds here, which are basically the highlight of Coulomb blockade transport in such devices. So this was done in the mid-2000s and 2010. And what people quickly realized is that doing these spectroscopy measurements, you could realize that the spectral properties of a single dopant in a nanostructure, in a nanotransistors, was quite different than the spectral properties which are usually obtained in bulk silicon. So that really raised the question of what is the impact of the nanostructure on the dopant properties. And an answer was given by basically combining this transport data together with an atomistic simulation framework. Back in the days, it was called NEMO 3D, which is basically a simulation package where someone can simulate the spectral properties of a single dopant, which is embedded in a full nanostructure that includes precise dopant position, presence of a gate interface, and also of electric fields. And what was realized at that time is that upon a finite electric field, the wave function of a single dopant that's brought close to an interface is actually distributed between the dopant itself and a quantum dot that is pinned at the surface of the gate electrode. So that really gives this hybridized regime between the dopant and the quantum dot that basically has spectral properties which are quite different than the bulk single donors. So it really shows you that combining transport data together with a modeling or understanding of the spectroscopy using an atomistic simulation framework was very useful to understand what was going on. I want to briefly talk about the susceptibility to internal lattice position for single dopant. So that's the idea that because of this valid degree of freedom, the exchange between two dopants can basically interfere as a function of the lattice position between the two dopants, and this interference condition is really extremely sensitive to the precise dopant position. So that means that if you move one of the atoms to the next site over, you can really have a drastic change in the exchange coupling between the two atoms. Unfortunately, in the usual devices, so transistor devices, for example, the actual position of the dopant is unknown. So that really triggered the idea to design an experiment where we could directly access this position and see the valid degree of freedom. So this was done using scanning tunneling microscopy, where basically we designed a single electron tunneling framework between a back reservoir to a single dopant and then to the STM, to a scanning tunneling probe here. And basically by moving the scanning probe in the XY plane, we can map out the wave function of the single atom, which is represented in this image here. And you can see that instead of having what would have like a single blob that would be the representation of a single 1s state, you can see that the image here is made of a very complex oscillatory pattern, which does reflect the presence of both lattice and valid frequency in the image. Like it was the case for the single atom transistor, we can basically compare this image to a theoretical image that uses that combines both atomistic simulation of the dopant and of the tunneling framework. And you can see that the agreement between two images is very good. And what we realize is that not only the agreement is very good, but this pattern is extremely sensitive to the exact dopant location in the lattice. So what we can do is to basically reverse engineer and start from the image and deduce the exact position of the dopants and work out what is the properties depending on where the atoms are. So coming back to the feedback loop, what I've shown here is that we've completed the loop once. So we started from this nanoscale transistors coming from the CMOS industry, where we can address single dopants. The way to address single dopants was to perform DC transport between the source and the drain, and to control this transport using the gate electrode. And we can basically understand this transport data by comparing them to a single atomistic simulation. So once we've done that, we can go through the loop again and again. And for example, the community has designed more and more complex devices and devices which are directly, which are really very much dedicated to quantum computation purposes. So I've already talked about silicon, the importance of isotopically purified silicon, and all the work that also aims to control what's going on at the interface between silicon and silicon germanium. But there's been tremendous progress also in the ion implantation work to try to make this implantation more and more accurate and more reproducible. In terms of lithography, there has been work to implement the dopant devices using 3D STM lithography. So that's also very important work. And there is also some material development around using strained silicon, both for dopants and for silicon germanium heterostructure. So here I'm going back to the feedback loop again. So you can see that from nanotransistors, there's been a zoo of material development to create those very exquisite devices for quantum computation. So now I'm going to move to the next step, which is to design electrical techniques to perform more and more complex operations. So one of the first development was to implement fast readout using gate dispersive readout on devices, on both quantum dot and dopant-based devices. So here an example of gate dispersive readout where a superconducting resonator was basically hooked up to the gate of this device to read out the quantum capacitance between two dots located nearby. You can see them with this dash square there. And this recently was actually performed directly on chip. So you have both the device and the resonator, which are patterned in the same, directly on the same chip, and to yield even better readout performance. There has been very important work to design H1 spin resonance and electrically driven spin resonance devices. So here's an example of a quantum dot device with a cobalt micromagnet that aims to create a magnetic field gradient to be able to rotate the spin degree of freedom using electric fields. And for the case of of dopant devices, we have access to the nuclear spin of the phosphorus atoms, which can be used the same way to design a flip-flop qubits and to perform electron spin rotations using electric fields. So that's also a very important step forward. And finally, we can also use a hybrid superconducting semiconducting technology to create, to couple the spin degree of freedom to the photon trapped in a superconducting resonator. So, and to basically achieve chip scale coupling between spin qubits. So here's an example from Princeton where we have one qubit trapped in the left double quantum dot there and another qubit on the right double quantum dot there. And this work aims to demonstrate coherent coupling between the 2 qubits using this microwave cavity there. And also very recently, there has been a very important work to try to control single electron trapped in quantum dots using a global field created by this dielectric resonator directly slapped on top of the device. So here's the brief summary, where coming from, again, the device point of view, creating very complex devices, and basically developing, also tying this to the development of fast electrical techniques to yield very complex operations. And finally, regarding the modeling characterization part, the way it's been moving on is to be able to investigate multi-electron systems from the theory point of view. So the same way we could image the wave function of a single atom, we basically push the experiment to be able to map the wave function of a coupled pair. And likewise, the theory was pushed to get the theory corresponding theory image using a full configuration interaction model that really takes into account the electron interaction there. And we can use the same FCI framework to dive into the exchange coupling between dopant-based devices for complex devices, which go beyond the simple single atom to single atom coupling. But it doesn't stop there. So recently, there's been also a huge push to develop machine learning algorithm and try to implement them together with spin qubit devices. And that's going to be very useful to tune the devices automatically using image and pattern recognition of the stability diagrams. And finally, there's also a very huge effort to develop complex protocols to characterize the performance of those multi-qubit devices through, for example, randomized benchmarking, and also to try to implement more and more complex protocols on those devices via pulse engineering or global field modulation. So that's really where this field is going. So here really kind of quick summary slide to highlight the fact that the loop can start from very simple devices, and by going through the loop over and over, we really are getting to very exciting multi-qubit devices that are giving better and better performance and are also more and more reproducible. So that's very nice. And I'm coming to the conclusion. So yeah, as I've been saying, we basically started from DC transporting transistors in the mid-2000s, and today we have access to multi-qubit devices on which we can do fast control and measurement operations. And we also have access to complex modeling and characterization tools to understand how does devices behave and to predict the next generation of devices. They're really very useful, and that was key to get to where we are today, which is to be able to achieve 99% fidelity on 2-qubit devices. That has been achieved in several groups in the world, and that really paves the way towards refining and implementing larger and larger scale architectures. So I give 3 quick examples there. So there's like an example of a modular architecture here, where we have some set of qubits which are in direct interaction between them, and these modules are connected to each other via a long-range coupler. People are also working very hard to try to design a CMOS compatible qubit module, and to also work towards refining dopant-based large-scale architectures. And basically this feedback loop, I've been talking a lot about dopant-based devices and quantum dot devices, but it doesn't stop there. This feedback loop applies to all the quantum states in silicon that people are currently exploring. So I give 3 quick examples there. The first one is to use acceptor or whole quantum dot to benefit from a large spin-orbit interaction and be able to perform EDSR. People are also exploring different atoms which have a higher nuclear spins that can be useful to use clock transitions between those between those nuclear states, and to design flip-flop qubits or complex flip-flop qubits. And very importantly, people are investigating rare earth and color centers in silicon, and those are very important, and I would say novel, because they own a telecom transition to make it compatible with photonic platforms, and it can also be very useful to design long-lived memories, quantum memories. So it reaches as a main message here that silicon has become a very versatile and a true leader for the development of quantum technologies. So that's there's been huge progress achieved in the last 20 years. So yeah, I think can't wait for the next 20. And that's it for me today.